It's so foggy I can't see. Fred, I think we've crossed the boundary into the land of boundary value problems. Look, here comes one now. Why, it's the diffusion equation. No wonder it's so blurry around here. Oh, hello, Fred and Jill. Pardon my tremendous hurry. I'm not just here on vacation, you know. I've come representing the distribution of heat in a rod over space and time. Oh, why, of course. But what are those zeros attached to? Well, I wasn't going too far, so I just put on my simplest boundary conditions. Got to run, sorry. It's because he's two functions, Jill, in a way. He needs initial conditions and boundary values because he describes space as well as time. I wonder how that works. Let's go ask the variable separator. Good idea. Variable separator, tell us how you have so much power over the simple partial differential equations. Yes, Fred, Gillian, I see your question. However, it is very simple, as I shall explain to you in this song. Just a moment. We assume there are two scales, one of time and one of space. The function u is made of two functions, which are multiplied in its place. We sub into the differential equation, and we get something like this. We divide on both the sides. So far, nothing is amiss. Now, both sides are always equal for all x and for all t. Yet these functions are independent. Equal to a constant, they must be. For t, this is a simple problem. We've seen it many times before. X likewise looks familiar, but its boundaries we cannot ignore. So that diffusion equation we met, he must have to satisfy both x double prime over x equals lambda, and x at 0 equals 0, and x at pi equals 0. Doesn't that? Wait a second. But what kind of equation would do that? What kind of equation would do that? What's its own second derivative, but equal to 0 at two places? I have no idea. We need some kind of a sign. You called, madam? Of course! The sine wave is its own second derivative and can be 0 more than once. Thank goodness, everything's solved then. But, dear lady, my employment is very particular. I won't work for just any separation constant. Squares of integer values only, I'm afraid. Oh, of course! Your inside has to be an integer, otherwise you'd be 0 again at the wrong place altogether. And if your inside is an integer, then lambda has to be that integer squared because of the second derivative. Quite so. Come with us, sine wave, and we'll go back and talk to the variable separator some more. Right here. Oh, you weren't supposed to stay here. You're supposed to exit. Oh, sorry. Okay, proceed. Variable separator, we found the equation that will work for the diffusion equation's boundary values. Aha, very good. But he says he'll only work for squares of integer values of lambda. Very true, so he will. But then, how do we know which lambda we have to use? Aha, the last verse of the song will answer that. There are infinitely many solutions to u sub xx equals u sub t. This means an infinite linear combination will solve whatever conditions there might be. Infinitely many solutions? Gosh! Doesn't that mean infinitely many coefficients too? Yes, of course. Now, variable separator? Phew! What an elaborate method for just one equation. Oh no, Fred. Separation of variables is the technique for almost all the simplest partial differential equations. Well, the ones that we can solve, at least. And the diffusion equation describes a lot. Don't forget, Fred. Ooh, hi, Fred. Oh, sorry. Don't forget, Fred. He can solve the distribution of heat in time and space. And if he were to expand to 2 dimensions, he would have a lot of power. Soon you'll probably run into the wave equation, too. She can be solved with these methods. But look, they're coming back. They are? Yes, they're coming back. Yeah, yes. Oh! Oh! Sine helped me find this, and I finally got it. Wow, but diffusion equation? How will you solve for all those constants? Bother. Well, I suppose that like an ODE, I'd better use my initial conditions. I haven't used those yet. Bother. Fred and Jill, if you want to help him, you might go see Mr. Fourier. He'll tell you how to find the coefficients. I can't help you with that anymore. Okay, let's go see Mr. Fourier. Wait for me. Excuse me, Mr. Fourier home? Yes, I'm coming. Oh, hello. What do you need? Well, you see, we brought this diffusion equation with us. After we found the sine wave, he found his solution set, but we still don't know how to find his coefficients from his initial conditions. I see the conundrum. Now, let me see the solution set you have. Right here, Mr. Fourier. Well, and what initial conditions do you have, diffusion equation? Well, I've got u of x and 0 equals to g of x, I believe, sir. What? Why, that's me. Well, let's set t equal to 0 first thing in your equation. That will give us u and x and 0 is equal to the sum from n equaling 1 to infinity of c sub n sine of nx. All that e business is gone. But I'll take another quick look. Say, ah. All right. Yes. This is a serious problem. A serious problem? Oh, no. A series problem. You'll have to use my series expansion to find the coefficients. You see, just about any function can be approximated by a sum of sines and cosines. In this case, only sines, because the boundary conditions are 0. And I'm g of x. Does that mean we'll have to find my approximation with sines? Quite so. But how can we find Jill's approximation with sines? Why, we hardly know anything about her. Except, I guess she's always been a bit odd, so sines should work okay. All right, Jill. Here's what we'll have to do. First, we'll assume that your sine series already exists. Let's get it out here. Ah, yes. There we are. Your sine series already exists. Now then, you remember that sines and cosines are orthogonal, yes? Of course. If you integrate their product over one period, it's 0. Now, sines of different frequencies have that same property, but sines of exactly the same frequency don't. So here's what we'll do. For each n, we'll multiply your sine expansion by sine of nx, integrate over one period, and take the average over the length of the period. Now, the integral of sine squared nx over one period is always 1/2, but every other term will disappear because of orthogonality. So we'll get this result. That should work out. But won't this take a long time? There's like an infinite number of those n's. Well, are you periodic and infinitely differentiable? Yes, I am. Then it should be no problem. Your coefficients will decay exponentially fast, and we shouldn't have to do too many at all. And when this is all done, my coefficients will be the same as the diffusion equations? Very astute, Gillian. You see what an important role boundary conditions play in partial differential equations. Well, time to integrate. Let's go, guys.